Now we want to look at an interesting part of physics this afternoon. Yeah, we want to look at sound. We want to look at calculations in sound. More importantly, we want to consider the relationship between frequency, sound, the tension on a string, particularly a sonometer, that's a string instrument, and length of that string. So we want to look at how these three parameters are related in a string instrument. And we are using sonometer as a case study. Then we now see how we can solve a problem that involves the three. Now, the first thing that we need to know is that the frequency of a sound, a note, is equal to n over 2l root t over a constant. Right. F subscript n is equal to n over 2l root t over a constant. This is a particular frequency. This is the length of the string. This is the tension in the string, and this is called linear density or mass per unit length. It is called linear density or mass per unit length. It is a constant, so we just have to know that. Now, for instance, if we have F1, then the equation becomes 1, that is n is 1 over 2l root t over linear density. Or if we have F2, what we have is F2, then we have 2 all over 2L, yes, root T over linear density, and that will be equal to 1 over L root T over linear density. And also if we have F3, then our n is 3 in this case, so the frequency will be n, which is 3 over 2L root T over linear density. So that's how frequency of a note, length of the string, and the tension are connected for a string instrument. Now, if we have a situation, let's say we have a fundamental frequency of 200 Hz in a string instrument, and we have the tension doubled and the length of the string also doubled. What will be the frequency produced in that scenario when the fundamental frequency is 200 Hz, the tension is doubled later, the length is also doubled? So what will happen? What frequency are we going to have in that situation? Now, let's take the formula. We know that F, from this equation we have that F, now Fn is equal to n over 2L root T over linear density. So from that, it is obvious that F1, that's times 2L1 all over root T1 is equal to F2 times 2L2 all over root T2. So we know these two cancel out. So what we have there is what? F1 L1 over root let me write it properly. So we have that F1 L1 over root T1 is equal to F2 L2 over root T2. That's all. So with this situation, we can always solve any problem. With this formula, we can always solve any problem that involves frequency, length, and tension. Now, we can apply that. Once we apply that, we solve the problem and we get a specific answer. Now, let us look at the problem now. We have that F1 there is 200 hertz. So that means 200 hertz times L1 all over root T1 is equal to unknown F2 times the length is double, so we have 2L1 now. The new length is 2L1. The tension is also double, that's root what? 2T1. So this is what we have. So we know that this cancels this. Yes. 2 here, 1, 2 here, 100. So we have 100 over root T1 is equal to F2 over root 2 times root T1. So root T1 cancel out. So we have F2 to be equal to 100 root 2 hertz. You can see how we easily found the frequency. That is just how it is. Just know our frequency of a note and the length of the string and the tension in the string are related, and you will always be able to solve the problem. They are just related by Fn is equal to n over 2L root T over linear density, and that's how we have it. And now finally, once you are able to bring everything down, you are going to have F1 L1 over root T1 is equal to F2 L2 over root T2. Thank you very much. I wish you all the best. Happy learning.